Hello friends, welcome back to the mathematical room. I am the caretaker Lucifer. So today we are going to see some special classes of rings. So this is the second section of the third chapter. Excuse me. So in the previous section, in the first section, we have seen some examples of rings. So based on those examples, we are today going to see some types of rings. So the section starts like this. We have seen in the previous examples that although rings are a natural generalization of rings are, they have been generalized from the integers. In fact, that was the first example. So although they are a natural generalization, they arise from the integers. Some facts about integers to which we have become accustomed need not be true in a general ring. This we have already seen. In fact, that's what we have been looking at in the previous videos. For example, we have seen the possibility of having A dot B equal to 0, where both A and B are different from 0. Natural examples exist where A dot B is not the same as B dot A. Okay. So based on these ideas or these observations, we are now going to define some types of rings. But before we do that, let us simplify the notation. What we are going to do is that we will not write A dot B as A dot B. We are going to drop this dot. So to simplify, we shall write henceforth write AB instead of A dot B. Okay, so this is A dot B. So let us now see what we are trying to define observing these things. So this is the first definition of this section. Let R be a commutative ring. Let R be a commutative ring. A non-zero element A in R is called a zero-divisor. Is called a zero-divisor if there exists again a non-zero element in R such that their product is zero. Okay, so that's what zero divisors are. Now, I should also perhaps point out that the term zero divisor that we have defined here, elsewhere you may find the same term meaning something else. Note that our definition defines a zero divisor only when the element is non-zero. However, some authors allow zero to be zero, the zero element to also be a zero divisor in some rings. However, for us that's not the case. So these things should be seen carefully. What we are talking about in the context of a given book. For us, zero divisors are by definition non-zero. And the next definition is based on this one, the previous one. Let R be a non-zero ring. R is said to be an integral domain if it is commutative and has no zero divisor. Sometimes people confuse this by thinking that it is a commutative ring with zero divisors. Okay, note this no carefully. If it is a commutative ring with no zero divisor, then it is said to be an integral domain. However, what about this non-zero ring? I should have actually mentioned this while discussing the examples themselves. However, let's just see this now. Look at this set which has only one element. Okay, it's a singleton set. Now we know from group theory that this is a group where the group operation is just simply this. It's not just any group, it's an abelian group. Any group having either one element or two elements or three elements or four elements is an abelian. In fact, five elements also. It's an abelian group. So this is an abelian group with respect to an operation that is defined like this. Since there is only A, so this needs to be defined, and we define it to be A itself. Similarly, if we define another operation, then with respect to these two operations where this is considered as addition and this as multiplication, this becomes a ring. This ring is said to be the zero ring. We say the zero ring because essentially there is only one zero ring. We'll see those things, okay? It's in the same sense like how there is only one group having only one element. So like that. So this is the zero ring. So our R is a non-zero ring, which means that our R has at least two elements. Typically we denote this element by 0. 0 because it's an abelian group, okay, where this is the addition and this is the multiplication. So our R is a non-zero ring. Should I say one more thing in this? Okay, let's just go forward with this list of definitions. So now we know what an integral domain is. So naturally enough, the integers form an integral domain, or I should say like this. The ring of integers is an integral domain. The ring of integers is an integral domain, as are the rings of even integers and natural numbers, rational numbers. Okay, so these are some examples of integral domains, the ones with which we are familiar well before studying ring theory. Now next, we see another definition which we have already seen before, but now we are formally defining it. A ring, okay, the thing that I was thinking of saying there while I discussed about the zero ring, I will say now after defining this. A ring R in which the non-zero, let me continue from here. In which the non-zero elements form a group under multiplication is called a, you know what it is, a division ring or a skew field. So we have already seen several examples of division rings, like the ring of rational numbers, the ring of complex numbers, the ring of real quaternions. Among them, the first two that I have just now said, they are fields. However, the last one is not a field. We have already seen that. Now some notations. Okay, but before that, I said I wanted to say something about the zero ring. Okay. Now look at this definition. A ring R in which the non-zero elements form a group under multiplication is called a division ring or a skew field. We understand this, but what is the consequence of this? In particular, what I am trying to say is this. What about the zero ring? If we consider this zero ring, is it a division ring? No. Why? Because the set of non-zero elements in this ring is the empty set. And empty set cannot be a group. So that's why the zero ring is not a division ring. Okay. Now look at this. If instead of this I defined skew field or division ring like this, a division ring is a commutative ring with unit element in which, okay, let me just write it and then we will see what is wrong with that definition. A commutative ring with unit element is called a division ring if every non-zero element in it has a multiplicative inverse. Okay. Someone may be tempted to define a division ring or a skew field like this, but this definition is not correct, because according to this definition, this is a division ring. How? Let us see. This is a commutative ring. There is no doubt about that, because the only product available in this ring is this. So which does not violate commutativity in any way. It is commutative. It's a commutative ring. Fine. It has a unit element. What is that unit element? Zero itself. How is zero a unit element here? You see, according to the definition of a unit element in a ring, suppose R is a ring, then an element 1 in R is said to be a unit element if 1A is equal to A1 is equal to A for all A. I am using the for all symbol here, okay? For all A in R. This is the definition of a unit element. Now, if I apply this definition in this case, in the case of this ring, with 0 in place of 1, do I have this? In this particular ring, now okay, let me write. Yes, I have, because for me now the only choice for A is 0, and I definitely have this. So this is a ring in which 0 is the zero element, of course, but 0 is also the unit element. And note that according to our notation, since we are denoting the unit element by 1, in this ring 1 is equal to 0. This may be confusing, okay? For some people this may be confusing. You have to understand that these are not numbers 1 and 0. This is the zero element of this ring and this is the unit element of this ring. So now this ring is commutative, it has unit element also. Now what about this condition? Every non-zero element in it has a multiplicative inverse. That means if A belongs to 0 in the context of this ring, if A belongs to 0 and A is not equal to 0, then A in okay, let me not use that notation. Then let me just use the language itself. Then A has a multiplicative inverse in this ring. Is this statement true? This statement is actually true. It is vacuously true because it's an implication. If this happens, then this happens. In this if-then statement, the hypothesis is false. So the statement is vacuously true. Okay. So according to this definition, this will be a division ring. But our original definition does not allow that to happen. Okay, so these two definitions are not the same, but some people may think that they are the same. So be careful with this false definition. It may trick you. Okay, so that was my point that I wanted to make. One more thing that I should mention here is that in the original text in Herstein's book, while defining an integral domain, Herstein does not mention that the ring has to be a non-zero ring, and that is a mistake because while proving a result, he implicitly used the fact that the ring is a non-zero ring without mentioning it. So that is one thing we should rectify in Herstein's definition. Okay, now moving on. Let's now look at the notation. We already know that by 0 we mean the zero element in the ring. Okay. And we shall denote the unit element in a ring by this symbol 1. Actually, sometimes if more than one ring is involved, say we have two rings, R1 and R2, both have their own unit, its own unit element, okay? Then the unit elements are denoted like this, one R1 and one R2, because they may be entirely different things, right? This may be, say, the ordinary integer 1. However, this may be the n by n unit matrix, okay, identity matrix. So the things are different. However, if no confusion arises, we are just simply denoting it by 1. And the multiplicative inverse of an element A not equal to 0. Yeah. We should mention when it exists, because in a general ring, in fact even in the ring of integers, not all integers have multiplicative inverses, only two integers have, 1 and -1. So when it exists and the multiplicative inverse of an element will be denoted by A inverse, A to the power -1. Okay, let us now quickly see that the unit element when it exists and the multiplicative inverse of a non-zero element when it exists, they are unique. How? Note that since a ring with respect to addition is an abelian group, the additive identity, which is the zero element, and the additive inverse of every element, which for every element exists, that's because it is a group, minus a, these are unique. That is because these are unique in the group. However, the multiplicative structure is not always a group. In a general ring, this may not be group. So that's why we cannot say at once from group properties that the unit element and the multiplicative inverse, whenever they exist, are unique. We have to prove that. In fact, it's just a simple observation, but let's just see what we are trying to say. Suppose there are two unit elements in a ring. One is 1 and another one is, say, 1 prime. I am using some other notation. Okay, one is 1 and the other one is 1 prime. We have to prove that 1 is equal to 1 prime. Now, if I look at this product, 1, 1 prime, then that is according to the definition of unit element. If I consider this 1 to be my unit element, then 1, 1 prime is equal to 1 prime 1 is equal to 1 prime. Thinking of 1 as the unit element, but I can also think of 1 prime as the unit element because that's also given to be the unit element. So then I will have 1, 1 prime equal to 1 prime 1 equal to 1. So from these equations I get 1 is equal to 1 prime. So the unit element, whenever it exists, is unique. Similarly, if I say have a non-zero element A and I have two multiplicative inverses, which I am denoting by these two symbols, I need to prove that they are equal. Here also a similar equation will now come. Let's look at this one. Yes. This is how I can prove this. A inverse 1 can be written like this. 1 A inverse 1, because 1 is the unit element. Now for us there is only one unit element, which is 1. Okay. And this is equal to 1. Now 1 can be written like this. A inverse 2A. A inverse 1. Okay, 1 is equal to this, because A inverse 2 is also a multiplicative inverse of A. Now using associativity of multiplication, we get A inverse 2 A inverse 1. So this becomes equal to what? Is equal to A inverse 2. Now A inverse 1 is again the unit element 1, because A inverse 1 is also an inverse of A, and because 1 is the unit element, I get this. So that's how these two multiplicative inverses are actually equal. If there exists at least one, that is the only one. Right. Now next comes the definition of our ultra important object, that of a field. This one is easy. A commutative division ring is a field. Okay. In the previous section, we have seen the division ring of the real quaternions and the following fields. Let me just simply write the rational numbers. The complex numbers and the integers modulo 7, right? In chapter 5 we study fields. Chapter 5 is only about fields, rather about field extensions. We will see those things. Okay, now now comes the a very elementary lemma, which is about how we can do some pretty easy calculations in a general ring. So without writing any more explanations or things, let me just straight away get to the lemma. So this will be lemma. What will be the number? 3, 2, 1. Okay, so this is the first lemma. Let R be a ring and A and B be any elements in R. Then number 1, minus A B is equal to A minus B. This is equal to minus AB. Number 2, minus A minus B is the same as AB. If in addition R has a unit element 1, then we have these two additional things. Minus 1 times A is minus A, and minus 1 times minus 1 is 1. So we now prove this lemma. The proof will not be very difficult, and the lemma also does not say anything deep. but nevertheless it's a useful lemma. It tells us that although in a ring some things are not how we expect them to be, like for example AB can be 0 or AB may not be equal to BA, but some things which we already are familiar with in the ring of integers, they nevertheless are true in a general ring also. So the proof goes like this. For the first one, oh, have I forgotten one thing? I think I have forgotten one. Yes, sorry about that. This is actually the second one, third one. The first one is this. Let me write it here. 0A is equal to A0 is equal to 0. So that means this will be fourth one and this will be fifth one. So first we have to prove this. Since 0 plus 0 is equal to 0, this is true in the additive group. We have